All right, good morning. So welcome back to pre-calculus here. We are going to talk again about exponential functions. So I know for people who are probably watching the videos, it's going to get a little monotonous, but I think hitting this thing twice, knowing how college algebra usually goes, I think that's probably not a bad idea. Okay, so it's going to be very similar to the first video. I don't know if you guys really want to watch this one too much, but it's always good to reinforce, right? So let's go ahead and take a look at this. So exponential functions, we have functions of the type y is equal to b to the x. All right, so this is different than polynomials where we usually have an x and then the numbers would be up here in the exponent, right? So this would be polynomials. And our exponentials flip it, all right? So the things about b, right, is that b cannot equal 1 and b must be positive. Okay, so the reason why we want b to be positive is because if we have like a negative number in here, all right, remember x is any number, right? X could be any number from negative infinity to positive infinity. So pick any number with a fraction in it, right? Specifically an even, right? The denominator that's even. So that would be something like negative to the 1/4, right? This would be 1 over the 4th root of -3. And this just isn't going to exist. Okay, this is not a real number. This is an imaginary number. Okay, and since this class deals with graphing things on an XY plane, we're not going to be able to graph this, and we have to go outside of the rules. We have to go outside the bounds to deal with this. Okay. So why can't b equal to be 1? There's two reasons really, but one reason is that we'd have 1 to the x, right? And that's a constant, right? If we had y is equal to 1 to the x, this would always equal 1. We already have constant functions to do that. The other reason is that we are going to equate exponents, right? And if we have 1 squared, and say, look, if we have 2 to the x and we have 2 to the 2, then what we're going to do is we're going to equate the exponents and have x equals 2. Okay? But if I do this, if I have 1 squared is equal to 1 cubed, 1 cubed, and if I go ahead and equate my exponents, then we have a mess. All right? So that's the other reason why we don't want b to be 1, is because this major idea of equating the exponents, it just ain't going to work. Okay? If you try it with logarithms next time, you'll see. When we get to logarithmic or properties of logarithms, then it's nonsense because we get 0 equals 0, and it's just as useless. Okay. So yeah, that's what we want for that one. Okay. Generally, right, if we have our y is equal to b to the x, generally the bigger the b, right, the bigger bend we're going to have. So every exponential function, it kind of looks like this. And we'll go through and do a table for it in a minute. But if your b gets larger, this bend gets far, far steeper. Okay, so b is greater than 1. This is what's going to happen. When b is less than 1, it's a fraction, but bigger than 0, but less than 1. Right, we're going to end up with something that's closer to a flat line. Okay, so as such, I'm going to pick something that is a little bit bigger than 1, but not much. Okay, actually, we'll take it midway. How about we do y is equal to something like 3/2 to the x. Okay, we could do 2 to the x. The arithmetic would be easier, but this is going to blow up a lot faster. Okay, 3/2 will blow up enough for our purposes, but there we go. And let's just make a t-table and see if we can graph this. Okay, so we have y is equal to the 3/2 raised to the x power. Okay, and here's our t-table. Let's do -2, -1, 0, 1, and 2. Okay, and I'll do all my, all of my arithmetic over here. Okay, so when x equals 0, we have y is equal to 3/2 raised to the 0. Right? And anything, well, anything except 0 raised to the 0 is 1. Okay, 0 to the 0 is, in calculus, you'll learn this is what's called an indeterminate form. Okay, and you don't want to mess with this just yet, kids. That's coming. Right? I mean, if you had to guess, I would say it's 1, but generally in calculus, you have a function to a function, and as it gets closer to 0, it may or may not be 1. So, be cautious of this next year. Okay, how about when x equals 1? Oh, but you'd never ask. Nice, easy one, right? So this is 3/2. I'm going to convert it to decimals because I want to graph it, and I don't want to have to deal with graphing something like that. X equals 2. Right, we have y is equal to 3/2 squared, which is equal to 9/4, right? If you're going to go off and do laundry and you have 9/4 in your pocket, you're probably not doing laundry, but, right, that's $2.25. Okay, when x equals -1, right, we have 3/2 to the -1. That's just reciprocal, right? That's 2/3, and we'll just call it 0.67. It isn't. Right, it's 0.6 repeating, right? 2/3 is probably the better way to go. But since I got to draw this on a graph paper, I'm not expecting my accuracy to be better than 1 decimal place. So, we can truncate for the sake of not having a terrible time here. So this is going to be 3/2 to the -2. That's going to be reciprocal. So we're going to write the reciprocal of 2/3 squared, which is 4/9. Which offhand is 0.44. Again, it's 0.4 repeating, but since I'm going to graph it, I'm not going to try to be that clever. Okay, important things. No matter how negative I get here, am I ever going to get a negative number? All right, if I put in a -3, a -4, or a -10, right? None of these are going to be negative, are they? They're just going to get smaller and smaller and smaller. So when you go to graph an exponential function, you don't have anything else, any transformations on it. You don't need a very big, quadrant 3 and quadrant 4 because you're not going down there. Okay, so we have, here's 1. Now let's make things bigger. Thanks. Okay, so here's 1, here's 2, it's 1, it's 2, it's -1, -2, all right? So let's go ahead and graph. So when x is 0, y is 1. When x was 1, we were at 1.5. When x was 2, we were at 2.25, so we'll put it up there. Okay. When x was -1, we were at 2/3. And when x was -2, we were about at 1/2. All right, so our function, right, this is going to get bigger and bigger and bigger, so we're going to curve upwards this way. And this is just going to get smaller and smaller and smaller. Okay, so we do have an asymptote, right, at y equals 0. Thank you very much. Okay, we do have a horizontal asymptote. Y equals 0. Okay, so be careful about that, right? And this will move up and down, right? As we do transformations on this asymptote will move up and down. All right. So we could do something like this. We could say, plug that in, y equals 0. All right. Yeah, and that's pretty much how you graph it. And this is all the shape, right? This is the shape of an exponential function. So you have your usual shapes that you had to memorize from college algebra. I hope you all did. And then we have this new shape that we have to add to it. Okay, you're going to learn one more in this class for logarithms. Okay, and then you're going to learn 6 more when you get to trigonometry. So you'll have a lot of shapes to memorize. Okay, and you'll pick up your favorites along the way as well. Okay. So yeah, now we can think about graph transformations. Okay. Before we get to that, we're going to say, what's our domain for y equals b to the x? Our domain is all of the real numbers. There are no x's I could put in here that's going to give me a problem, provided my b was properly, picked. And my range, you don't see any negative numbers here, right? We kind of went through and did a big negative numbers, and we never got negative. So my range, right? Does it hit 0? No, I'm afraid it doesn't. So that's why we end up with the parentheses. All right. So that is our right. That's our idea of what an exponential function looks like. Okay. Now let's go ahead and put in some transformations. All right. So what if we do a vertical transformation? Why is it actually? Let me take a look at your book. Okay. Let's see here. Oh, it did too. Okay. So they did 2/3. Okay. All right. Let's take a look at this one and say we'll do 2 different ones. Right. We'll do a vertical and we'll do a horizontal. Okay. So we'll do a y equals 2x minus 1. What was that? A minus 1. Yep. Okay. So right, this guy here, this is a vertical transformation. It's a vertical shift. We're going to be moving 1 unit down. Okay. Now, this one is a little tricky. Okay, it is a horizontal shift, right? And it's opposite, so you're going to remember and say that this is going to be 1 to the right, right? This technically is. This is a horizontal shift to the right. It is also a vertical shift, it's vertical compression or expansion. Okay, there's also a vertical compression because we could do this, right? We could say y is equal to 2x minus 1, which is equal to 2 to the x times 2 to the negative 1. So this is 1/2 times 2 to the x. Now, be very careful when you're dealing with exponential functions because can you combine those two? No, because remember your PEMDAS, right? Where's exponent? It's up here. It's way before multiplication or division. So we got to deal with the exponents before we deal with this thing. So you cannot combine these ever, right? To make a new base. You have to go through and do the exponent stuff first and then the multiplication. Okay. Or if you wanted to keep it the way they wrote it, technically there's a parentheses there. Okay, nobody ever writes it, but there is technically a parentheses there. So we do the parentheses first and then raise it to that smaller exponent. Okay, so be really careful when you see this. Okay, this is a standard problem I would love to give is do something like, what is 3 times 2 to the x? And, is that equal to 6 to the x? Like, no, that is not the same. All right, these are way different. They're both exponential functions, but they're not going to look alike. All right, so be careful about that. So back to where we were. We were looking at vertical and horizontal shifts. Okay, so if I'm looking at something just like 2 to the x here, right? So my vertical shift goes 1 down. So I'm going to take every point I have here and move it 1 unit down, right? 2 to the 0 would be, or 2 to the 0 would be 1. And then we're going to move that down 1. So it's going to be here. Okay. Usually my vertical asymptote, or my horizontal asymptote was at y equals 0. This gets moved down 1 unit. So y equals -1, right, is my vertical asymptote, or my horizontal asymptote. All of the negative values here, they're all going to be fractions. When I subtract 1 from them, they're all going to be negative. So even though I said, well, they're not going to be negative before, but that was without a vertical shift. Now we have a vertical shift. This is going to be, right, this is going to move down and do something like that. Now we just handled the 2 to the, we just handled that. We did not touch this thing yet. Okay. What this is going to do, right, this is going to move us 1 over to the right. So really we're over here. Now this asymptote stays the same. Okay, but all of this stuff over here, okay, all of this stuff over here moves 1 more unit over. All right, so that's what we have to do. But, right, this is also a vertical compression. So if we're going to take this, we're going to, right, we're going to, well, not this one is a bad example, but we're going to go, oh, actually no, because we would do that first and then do this. So we would take 1, you know, if we put in x equals 0, we get 1/2 2 to the 0 minus 1. Evaluate this, and we would get 1/2 minus 1, which is there. So we would move this down a little bit here, right? And that would take care of everything because we would have moved over that vertical shift there. Okay. So my drawing is probably not doing anywhere near to the kind of justice that should be done here. So we'll go over to the book and let happen what happens here. So here we have the domain and the range. Okay. Oh, we're going to use transformations first here. Okay. So we're going to go ahead and take this and we're going to move it down 1 unit. And then we're going to go over here. We're going to move it over 1/2 unit. All right. Oh, they don't give us a chance to do that. All right. Well, actually, we're going to move it 1 unit here first and then down by 1. And that should give us a better choice. All right. Now, am I allowed to say? It's not going to like it. Oh, it did. Okay. I'll show you a trick for the asymptotes. Okay. When we get to a more clever one. Domain. Well, the domain for every exponential, right, is negative infinity to positive infinity. Transforming it and going to change that. Okay. But the range, now the range is a little bit different because we went down by 1. Okay. So we're going to be going down to -1, right, instead of 0, and then up to infinity because that's not changing anything either. All right, we're at the equation of the asymptote. The equation of the asymptote, y equals -1, because we moved it. Everything gets shifted down by 1. All right. Let's see. All right. This transformation is actually one of the important ones. Okay, this is 3 to the x. They want to do a 3 to the x and then 3 to the -x. Okay, so how about we try this? All right, we have y equals 3 to the x. We have y equals 3 to the -x. Okay, before I go through and do this, all right, do you remember somewhere in the past you had a property that had an exponent to an exponent and you multiplied them together, didn't you? You said this was a to the rs, right? Well, this works in this direction too. So because I have 3 to the -x, that's rs. We can say that this is 3 to the -1 raised to the x. All right, so this is 1/3 to the x. That's what this negative in the top here does to this thing. Okay, so really this is the same as 1/3 raised to the x. Okay, so if we go through here, right, we have 0, -1, -2. We have 1 and 2, right? When x is 0, it's 1. This is 3, right? 3 to the 1 is 3. And 3 squared is 9. We can keep going, right? 27. Keep going. This side, right, is 1/3, and then 1/9. Okay, just take the reciprocal because that's where we are. Now, this function, right, is 0. Oops, I'm not trying to make a number line. I'm just trying to make a t-table. Sorry about that. All right. So we want 0, 1, and 2, -1, -2. So again, a reciprocal, right? 1/3 raised to the 0, still 1. 1/3 raised to the 1, 1/3, or 0.3. I know it's repeating, but again, if we tried to graph it, this is the best I'm going to get. Put 2 in here, we get 1/9, which is going to be 0.1. Okay. Take the reciprocal. This was 1/3. The reciprocal is 3. Reciprocal, the squared, right? When x is 2, we have 1/9. Reciprocal is 9. Notice that these are all reciprocals of each other. Okay. So when I go to graph this thing, right, here's my 3 to the x. Oops, not 3x, 3 to the x, right? 3 to the x. And here we have 3 to the -x. So you can see that they are, they're doing what the negative sign is supposed to do. It's supposed to flip it around the y-axis. So that's what we got. But we also have a reciprocal thing going on. And it's just kind of a neat sort of relationship that e to the x, or 3 to the x or 3 to the -x has. Okay. So if I try to graph this thing, okay, so we're just gonna flip. There. That's all we wanted to do with this. Okay, they didn't give us any other transformations to deal with. They just said k is equal to 3 to the -x. Like, great. The domain, same as always. Right? There's no things that come out here. And the range, okay, look at my range. Just because it's infinity down to 0, but we still rate it from smallest to largest. Okay, so we still have a 0 to infinity kind of a problem here. Okay, so we still have 0 and then to infinity, and there we go. Okay, great equation for the asymptote. Same asymptote, nothing changed. You only change the asymptote when you're going to get a vertical shift. Okay, you don't have to change it any other time. All right. Let's talk about ease for a little while, because I know that is always a delight when you're first learning this. Okay, and I know we went over this last time. I don't think we need to go through the numerics for it. Right, for e. I'm going to say see last video, but it was 1 + 1/x raised to the x as x grows without bound. You'll learn a slightly different way to write this in Calc 1. Okay. But just put as big of a number for your x and then keep going. Put a bigger one in, put a bigger one in, put a bigger one in. All right. And e, that was approximately 2.7, and then 1828, 1828, and then there's like a 5 after that. Okay. If you ever wanted to, like, what's e? Like, can my calculator do e? Oh, it sure can. So if I just want e by itself, okay, and usually you're going to see this in context of an exponential function, okay? So if I go through do my second function, notice it gives you an e with a caret because it's almost always something up here, okay? But if we just type in 1, right, e to the 1 should just be e. right? And there you go, it's 2.718. Subtract 2 from it and see if we get any bigger. See? 2.718281828.5. That's actually rounded. It's actually 4, but you know, we're not going to worry about that. I doubt anybody will ask you to you know, any significant amount of decimal places. Just like it's probably not worth your while to know pi to, you know, whatever decimal places you want to know it to. I mean, to 2, it's probably enough. All right. And the reason why your calculator does this is because the function y equals e to the x is such an important function when you get to calculus. And the reason why is that you're going to be dealing with exponential functions. And when you want to do calculus on exponential functions, you have to remember that there's a scaling factor. Like 2 to the x, there's a scaling factor. 1.063 to the x, there's a scaling factor. Okay, so be real careful about that. And that is exactly why, if you're in calculus or physics or finance, you're in a science that measures chemistry, you're in a science that measures how things change, you want e to the x because you're going to do calculus on it. If you are just trying to measure things like, well, how big do they have to be, right? Or it's the age of this thing, like I'll just measure change, but not the same way that physicists do. Meaning they don't typically do calculus. But you could get away with, like, you know, 10 to the x, right? Because we have 10 digits, 10 fingers, so this is the usual operation that we deal with, right? Or whatever other number seems to be most appropriate. Okay, if you're dealing with a percentage change or a percentage, you know, percentile model, you're often going to be dealing with something like that. Okay, same with biology. Okay. So, you know, if you have a population growth, right, and say you have a population growth of like 5, let's make it smaller than that, right? You have population growth of like 81%, right? The way you're going to do this is you're going to say 1.01, that's your population growth to that, and your usual model is going to do something like this, okay? 1.01 raised to the x power, that's like a population model, okay? They don't usually expect you to memorize these things. They'll usually give you, you know, population growth according to this model, and then go for it. But population growth of 1%, that's where they got this. Okay. You could also do population decline of 1%, right? Pop decline, we would say 1 minus 0.01. So we'd have 0.99 raised to the x. So let's see here. Can I do this? Can I do a Desmos thing? Okay. I don't want them. Can I just do Desmos.com? There we go. No search for it. Lord. All right. So we have, what do we have? We have y equals, come back here. Y equals, say, 1.01, 1.01 raised to the x. All right. And then we'll have y2 is equal to 0.99 raised to the x. You'll see it's very, very tiny amounts, which is why you want what's going on here. But you can see, like the red one, right? It's still got that exponential form to it, even though you have to go out a ways to do it. Same thing with, if I change this to 5, that might be a lot bigger. You guys could see that a lot more. 0.95. Okay. Oops, not times x, to the x. All right, so let's go in a little bit here. So you can see I changed a lot faster, all right? But we still end up with the same idea here, okay? And if you put in y is equal to 1.05 to the negative x. Oh, that's a bit different. Okay, let's not do that. Okay, so not the same. Okay. But close. So, so yeah, this is a decay, this is a decay function, right? Y2 is a decay function. And then, so if you're losing population, this is what you're going to look like. And if you are gaining population at 5%, then this is what you're going to look like. All right, so that's an idea there. Okay. All right. So important to remember how exponential functions work. A lot of times, if you're going to go into your sciences, you can think about doubling times. We'll get to solving a doubling time when we get to solving equations with logarithms. But if I tell you that there's a doubling time, so if you have a population of 100, when is it going to be 200? Okay. And this was a really nice way. If you're ever going to go into, like civic planning, or if you're ever looking at biology, doubling time is finance. Doubling time is an important concept. So you might have a doubling time, right? So say you have a population rate, right, or population growth rate of, say, you're studying humans, and you have a doubling time of 20 years. Well, understand, if a town has a doubling, it's going to double its population in 20 years, and you're on a planning committee, you better start building, because everything is going to happen. We're going to need twice as much of everything because we have twice as many people now. Okay, so if you have a certain amount of water, you better make sure you can have water for double the people. Right, that's probably going to require more purification plants. It's going to require other things. Traffic, right? If traffic is bad now, in 20 years, it's going to be twice as many cars on the road. So when you're thinking about population growth, I'm like, oh, we want a high population growth. We're going to double in 20 years. Like, if you're not building, you're screwed. So that's why you don't want a high population rate growth. You want it manageable. But if we have 40 years to double, that seems a little bit nicer, right? You have 40 years to build twice the number of roads because you're going to have twice the number of traffic in 40 years. You have a solid waste problem. Well, in 40 years, you're going to have twice that problem. So you better figure out what to do with your trash. Okay. So that's what we have for that. Like I said, we'll go in more into this when we start solving for them. But that's an interesting way to think about population growth or exponential functions in general. Okay. So let's see here. We were talking about E. Very good. So one of the things you might have to do, right, is E to the, and they're just going to give you a number, and they're just going to say, hey, what's E to, like, say, the -2? Well, that's 1 over, right, E squared. But you don't have to worry about that. Your calculator is going to handle that for you. Okay. So we could say second function. So this is all you have to do. Second function, ln. We're just going to make sure it's this negative. It's negative on the sign for the calculator. It's not minus, it's sign. Okay. Calculators actually have a very big difference between minus, which takes 2 numbers, versus changing the sign, which only takes 1 number. If you type this one in, they're going to expect 2 numbers. Okay. I'm sure all these numbers are delightful because they're all irrational. Okay, they're fine, but it's not for most math. Like, we don't really care what this number actually turns out to be. We just know it's either the -2. We stop there. If you're an engineer, you're going to care. Okay, how many decimal places you want to go out. But until you know the context of the problem, you don't have to type out so many decimal places, right? If you had an E cubed, right, second function ln, or E cubed, there, 20.0855, keep going. Okay, so just as a hint for the folks that are going to become engineers, it's really important to know how many decimal places you're going to go with. Don't always go with 2. Okay, because here's thought for you. If you are, building something and you have to order tons of concrete, right? And you tell the operator, hey, I'm going to need 20.09 tons of concrete, they're going to laugh at you. Okay. If you need more than 20, then whatever the next unit up from 20 is what you're going to order. So 20 plus, like 20 ain't going to hack it, right? You need more than 20. What's the smallest increment you can go up? 20.25, 20.5, 21. That's going to suck because you're going to have 9.92 tons of concrete laying around. But, you want to ask, like, if I need more than 20, like, what's the minimum amount I can order up to 20? But if you call up and tell them I need 20.08, like, no. Okay. If you're putting in something in your house, right, and you could say, hey, I'm going to need 20.09 cubic. Well, I put 20.09 cubic feet. That's a lot of earth. So you're like redoing like an entire farm for that. But still, the person that's going to, load up that truck and they deliver this to you, they're going to laugh at you if you say 20.09. Okay, you want to pay attention to your units and make sure you're ordering the right amount from the person you want to do. Now, if you want somebody to cut a wire for you, you could probably get away with something like, I need 20.08 centimeters of wire, and then or 20.09, and they'll cut it to a tolerance. But be careful about that because, the last thing you want to do is you'll make a mistake. Everybody makes this mistake. Everybody makes mistakes on their first job, the first time they do something. So don't beat yourself up too much with that. But yeah, that's E. It's just a number. E is just like pi. I mean, it's similar to pi, where I want to put an equal sign there. It's close to 3. It's a little bit less. Pi is a little bit more, but you don't want to don't let this number scare you. Okay, we just don't have a good symbol for it, so we used E. Same thing with pi. We don't have a symbol for it. Well, we do have a symbol, but we don't want to represent it the same way we represent other numbers because it doesn't fit. It doesn't fit in the scheme we have for numbers. So that's what we could do with E. So just don't be afraid of it. It's fine. Okay, it's just 182.8, 182.8, 5, and then it keeps going. One of the other ways that I like to do with E is just off to an aside, 3 factorial, right? That's 3 times 2 times 1. Okay, that's what, excuse me, that's how we deal with factorials. So if you get 20 factorial, right, that's 20 times 19 times 18 times 17 times all the way down to 1. 0 factorial, that's defined. That's where we use 3 equal signs. That's just 1. Okay. But I always like dealing with E is equal approximately, right? Well, if you go out far enough, see infinite series, there are infinite value, infinite pluses, we're going to be okay. So it's 1 over 0 factorial, 1 over factorial, 1 over 2 factorial, 1 over 3 factorial plus. Okay, keep going. And that to me, this helps me get a grasp or get more comfortable with E rather than this business of 1 plus 1 over n raised to the n. Okay. When my teacher introduced it to us, he also taught us this one. You won't appreciate this until about halfway through calculus. Here's a function. This is y equals 1 over x. So if I start with 1, okay, if I'm starting here at 1, so this is the value I've got, 1 to some value, I don't know. Okay, if I want to paint the side of this thing, okay, so we want to paint this thing, want to paint the side of this function. Okay, we'll paint it in green. And I've got 1 can of paint that I use to paint this with. The place I run out, that's E. Okay, so the area between 1 in some number, it's going to be E. Okay, when I've got this area to be 1. Okay, where I actually not, that's not E. The area is 1. What am I doing? The area is 1. The place where I'm going to stop when that area is 1 is E. See, I botched it. I made this thing as confusing as it is. I made it even more confusing. If we go from 1, we paint 1 unit. The place where we end that paint is going to be at E. You say, why would anybody think of it that way? That halfway through calculus, like, oh, that's what that means. So there you go. Actually, more than halfway through calculus. But there you go. That's another way of describing E to people. Okay. But usually that way and this way, those are your 2 standards. Okay. Yeah. And all the regular stuff works, right? E to the x, it still looks the same. Right? We still have an asymptote at y equals 0, a domain, negative infinity to positive infinity, a range, 0 to infinity. Okay, all the stuff that we just did with every other exponential functions, same thing. Okay, same idea. So let me see, what else do we want to say about E? Not a lot until we get to logarithms, which will be tomorrow. Okay, because we could use it as a base. We'll still be using it as a base. All right, but I'll let you go with that. Oh, you know what? Let's do a compound interest problem. Okay, so here's the formula for compound interest. Let's go with A for amount is equal to the principal 1 plus R over N raised to the NT. Okay, this is compound interest. This is the actual formula that the banks use when they want to screw us over, right? Or when we're putting money into save. So this is the actual formula that is used. If you get unrealistic things, you probably made a mistake. Okay, unless the problem is bizarre, unless the problem is absurd, you're going to end up with, you know, an absurd answer. So if we wanted, okay, so, you know, maybe you want to save, you want to put money in a CD, right? That's a certificate of deposit. A certificate of deposit, you go to a bank, ask them for a certificate of deposit or a CD. You're going to put in a certain amount of money. They usually have minimums, like $500. They pay a little bit more interest than a savings account do, but you can't take your money out until the term is up. And the terms are usually, so it usually lasts, I think the smallest ones will last 3 months, so a quarter. But usually they're 6 months, a year. There's 5-year CDs. Okay, so if you know, like, hey, I'm putting this money away for a car, I'm going to be able to buy the car when I'm, you know, in 5 years, that's when I'm expecting this, and you want to get a little bit more interest on your money rather than just putting it in a savings account, that would be your choice, because you're not going to lose anything because it's still just a savings thing. So it's still insured by the bank, the federal government. But it's usually not as much as, if you're saving for retirement, don't do this. Okay, this is a terrible idea to save for retirement. But if you want to save for something that's you're going to have to buy in 5 years, you know how much it is, then this might be a better way to go, to put your money somewhere, because it'll, you know, it'll get a little bit more interest. So let's go ahead and we're going to make a 5-year CD. Okay, and you could go to like bankrate.com and look up interest rates for 5-year CDs. Okay, that's something that you could do. Let's go ahead and say that we're living at a time where our interest rate is 3% APR. Okay. Usually at this point, savings rates are insulting. Okay, but so 3% is a lot. But they used to be 3%. So we'll go ahead and do that. And let's say you've got $2,000. Okay, this is all pretend because this right here made it complete fiction. So let's pretend you got 2,000 bucks. You would put it in a 5-year CD because maybe in 5 years you're saying, okay, well, I have to move out of my house then, and I need a car. So this is the maximum amount of money I have. Can't buy a car right now, so let me put it away and see if I can get something in 5 years. Okay, how much money would I have? How much money would you have? So we're going to say, okay, well, A is equal to, and we have our 2,000 bucks, 1 plus, and we'll say compounded monthly. That's pretty standard. All of these things you have to be given. Okay, you're not doing this problem unless we tell you all of these pieces. Okay, here's the mistake everybody makes. It's 3% APR. So we're going to put another 3 there. Okay, and number of compounding periods. All right, and then we're going to have 12 compounding periods per year for 5 years. Okay, so that's my NT. It's number of compounding periods times year. And then we're just going to run this through the calculator. Okay. Typically, I don't put this part in the calculator because there's a lot of parentheses you got to keep track of. I'll just write down 60, right? Because 5 times 12 is a little bit easier to deal with than trying to deal with that. All right. And then how much do you think you're going to get? 3% interest on $2,000 for 5 years, right? So that's going to be what? $30, $60 a year for 5 years. So what are we going to have? About $300? Let's see. If I did it with simple interest. Okay. So we're going to have 2,000 times parentheses 1 plus 0.03 divided by 12. Okay. Caret raised to the, I'll say 60, but I'll just do 12 times 5 here, just to emphasize the fact that when you put this caret in there for the raised to, you got to make it a parentheses unless it's a single number. Okay. And our answer, 2323.23. So that's kind of what's expected. I said, you know, what are we going to make? $300 bucks? Like, yay, because we put it in a compound interest thing, we made $23.23 more. Okay, delightful. But that is the formula you use. If you ended up with like $20,000, like, please come back and tell me if that looks normal to you. What bank can you 10 times your money in 5 years? I would love to know that. It would make saving for retirement on my part so much easier. Okay, so if you're getting unrealistic numbers out of here, okay, and I understand a lot of you guys are young and you don't have a good experience for what's younger or for what's realistic. But just imagine, like, if people were making 10 times their money in 5 years, like that would be it. We wouldn't have to worry about anything. Okay, you know, life would be a lot easier for a lot of people, because I think even at 17 or 18, I think I found like I started working then. And I think after a couple of months, because when I worked there, that was my minimum wage. But even after a couple of months, right, you save up about $200. You save up, you know, and you can usually find a bank that has like CDs or savings unions, savings union to find smaller amounts of CDs. At least you could back then. Maybe now it's 500 is the minimum. But if you could make 10 times your money in 5 years, that would be too good to be true. So if you get, let me show you what happens. Okay, if you make the mistake, it's 300% interest, by the way. Okay, at this point, you're not saving, you're a loan shark. Okay. So this is 2,000 times 1 plus 3 over 12. Okay, and then raised to the 60. All right, now let me show you what happens. All right. That is a lot of money. So if you, what do we end up with here? 1,305, let's do 1,305. All right, 060. Okay, 894. So what is that? Thousands, then we have millions, and then billions. Okay. So if it looks right to you that you could put $2,000 away for 5 years and end up with $1 billion, I really need to know what you do with your life, because that would be great. All right. So when you get answers like this, realize you've made a terrible mistake, and it's right there. Okay. Counterpoint: if you go to a loan shark and he says, "Okay, I'll just, charge you 300% interest, pay me back in 5 years," prepared to get both your arms and both your legs broken, because you ain't gonna make it. Okay. All right, we're gonna stop there. You have a lovely afternoon, and I will do my best to put this up sooner rather than later. Okay, so I'm gonna stop recording.